For problem number 4, we've got a charge on capacitor C1. It's 9 microfarads. C2 is 18 microfarads. And the voltage on the battery is 120. Initially, we've got all the switches open, and then the capacitors are uncharged. And then C1 closes after a long period of time. All the voltage, the positive voltage on the top of this battery will move to the positive side, and then all the positive charges will attract the negative charges from the side of the battery. So we end up with a full 120 volts that is transferred from the battery to the capacitor. So in this scenario, we are trying to determine the charge on capacitor 1. If I use this equation, which is charge over capacitance is equal to voltage, then the charge is equal to voltage times capacitance, which is 120 times 9 times 10 to the negative 6, and that gives me 0.00108, and the unit for this is coulombs. Okay, question B is going to be the scenario where the switch is now open and switch 2 is closed. So what happens here is that the capacitor, which is in parallel with the battery, even though it's disconnected, capacitors in parallel have the same voltage. And we also know the equation for voltage is equal to Q over C. So if my charge on capacitor 1 is Q1, and my charge on capacitor 2 is Q2, then the Q1 over C1 and Q2 over C2 here equal each other because the voltage drop is the same. Now we can't make the assumption that the voltage drop is 120. It definitely isn't because it's attached to the it's no longer attached to the battery. But and we also can't make the assumption that the 120 volts that was originally on C1 is going to split between the two because potential is not conserved. So in this scenario, we have to just figure out what that voltage is based on the fact that the charge over capacitance of each of those capacitors is going to be equal. So what we also know is the fact that the total charge, which we calculated in part A, Q total, is equal to the charge in Q1 plus Q2. That's conservation of charge. So as it transfers, we know that some of the charge is going to go to C2, some of the charge is going to go to C1, depending on the capacitance. So what we can do, because we do know what Q total is, and we have too many unknowns in our equation up here, is we can substitute. Let me actually do this work down here. We can take our Q1 over C1 and set that equal to Q2, which Q2 is equal to Q total minus Q1 divided by C2. And now we need to isolate the Q1 because the Q1 is unknown. So in this scenario, let me actually multiply both sides by C2. You can do it multiple ways. And then multiply the other side by C1. And then I'm going to distribute. And then I want to bring my Q1 to the other side. And then pull out my Q1. So Q1 is equal to Q total times C1 divided by C2 plus C1. I have all of these values. Q total is from part A. C1 is 9 times 10 to the negative 6. C2 is 18 times 10 to the negative 6 plus 9 times 10 to the negative 6. So when you plug all of that into your calculator, Q1 is going to equal 3.6 times 10 to the negative 4 coulombs. Okay, so if I go back up here, I have a charge of 3.6 times 10 to the negative 4. And I don't think it asks for part B, determine the potential difference across capacitor 1. So it doesn't ask me for the charge on capacitor 2, but I know that if I subtract Q1 from the total, I could get the charge on capacitor 2. Instead, we're asked for the potential difference. And delta V is equal to Q over C, which is equal to 3.6 times 10 to the negative 4 all over 9 times 10 to the negative 6. And the answer to that gives me 40 volts. Okay, so what we know here is that if this is equal to 40 volts, then this is also equal to 40 volts. And the last part, D, is if the switch remains closed and now S1 is also closed, how much extra charge flows from the battery? So what we've got is, in this scenario, I'm now closing this switch right here. Now, if I want the extra charge that flows in, I need to figure out the equivalent capacitance. So I'm going to try to squeeze in part D over here. I probably will make this messier than it needs to be, but for part D, I'm going to rewrite this circuit so that I just have one capacitor in series with my 120 volts. And because the capacitors are in parallel, the C equivalent is going to be 9 plus 18 microfarads. So that gives me 27 microfarads. The charge for this is equal to voltage times capacitance. And I end up with a charge equal to 0.00324 coulombs. Now that's not my final answer. That is the net charge that goes in to the full circuit with the two capacitors. I originally started with a total charge of 0.00108. So if I want the charge difference, the extra charge that comes in, then I need to take this new Q and subtract it from the original Q, which is the Q from part A. So I'm going to take my 0.00324, subtract it from 0.00108, and my extra charge would be 0.00216 coulombs. So this would be the answer for part D.